Okay, welcome back. We have already discussed S equals R times theta for the distance, the arc length. What we are going to now discuss is if there was a point on the circle, how fast would it move around the circle? Or if I were to rotate a circle or say a tire, how fast is the angle changing? So the measure of how fast S is changing is called linear velocity. Or how fast a point is moving on the circumference of the circle. Okay, so linear velocity is going to be in some sort of distance over time. And since we're moving around an arc, it is going to be length over time. And that's very important to understand the units for linear velocity. It's going to have some length, feet, inches, miles, over some unit of time, hours, seconds, minutes. Okay, they're not always going to tell you this is your linear velocity. They're going to say a point is moving 5 inches per second around a pulley. Because it's inches per second, you need to relate that to the linear velocity. Okay, now the variable for linear velocity is v. That is the variable for linear velocity. Okay, it's the distance traveled, the arc length divided by the time. Well, we've already learned that arc length is the same thing as r times theta. So this is just another version of this. Okay, and then another version, which is the one we're going to use, if you take theta divided by time, the angle divided by the time, that's called angular velocity. See, theta divided by time. Angular velocity, and this little Greek letter here is called omega. Okay, so we're going to have capital V for linear velocity, and we're going to have omega for angular velocity. So the measure of how fast theta is changing is called angular velocity. Okay, and for angular velocity, radians per unit of time. So in order for you to call it omega, it has to be in radians per unit of time. Revolutions is not the same thing as radians. We would have to do a unit conversion from revolutions to radians. 1 revolution is 2 pi radians. Theta, again, just like before, theta is always in radians when using these formulas. Okay? So it says we always use radians as the unit of measure for theta. However, sometimes angular velocity, in layman's terms, is revolutions per minute or degrees per second to give a better understanding of how fast the angle is moving. So to make calculations with the above formulas, a unit conversion may need to occur in step 1. Okay, so here are the steps that I'm going to go through that you can always refer to. And we're going to do a dimensional analysis that you should be used to from science chemistry class. Okay, so we're going to write down all the information that's given to us. We're going to pick the equation. We're going to rearrange the equation first, and then we're going to use our tables, T-charts, railroad tracks, whatever your teachers have called them in the past. Okay, I call it a bridge. Okay, you also need to make sure you show how your units cancel, very important, and make sure that's included in all of your work. Okay, so that's going to be the work required for the story problems. Okay, so let's go ahead and look at example number 1. A cylinder with a 2.5-foot radius is rotating 120 RPMs. That's rotations per minute or revolutions per minute. That's not radians per minute. Okay, so let's go ahead and write down the given. the radius, so r equals 2.5 feet. Now, 120 revolutions per minute. What variable is revolutions per minute? Well, none of them are revolutions per minute. None of them are rotations per minute. However, they are trying to give us the angular velocity. So that's where the unit conversion has to take place. In order for us to call it omega, we're going to take our 120 revolutions per minute, and we're going to multiply that by, we have revolutions we want canceled, and we want radians. So 1 revolution is 2 pi radians. So our omega, or our angular velocity, is 120 times 2 pi, so that's 240 pi. We can leave it exact for now, and that's radians per minute. So that's what was given to us. So we have to do, sometimes if it doesn't say radians, you have to convert it to radians in order for you to call it omega. All right, so now let's answer the question. Question A, give the angular velocity in radians per second. Okay, well, we have the angular velocity. It's 240 pi radians per minute. But it wants it in radians per second. So we want the minutes to cancel. And we want to be left over with seconds. So 1 minute is 60 seconds. And again, you can leave your answer in the form of pi. That is very standard to do that. So if we go ahead and we reduce 240 divided by 60, that's going to be 4 pi. The minutes cancel, and we're left with radians per second. So that is the angular velocity in radians per second. Now they want the angular velocity in degrees per second. So I'm going to take my radians per second, and I'm going to do another dimensional analysis. I want to get rid of my radians, and I want to have degrees. So what did we use for that conversion? Pi radians is 180 degrees. Okay, and the pi's cancel, and we are left with 4 times 180, which is 720. And what units? Degrees per second. So that's how you're going to show your work, nice, neat, and organized. You're going to show how your units cancel. Okay, and a nice little bridge. Okay, now we're going to do part B. Find the linear velocity of the point on its rim in miles per hour. So the formula you need to memorize is linear velocity equals the radius times the angular velocity. And they want miles per hour. So we're going to start with our radius. Okay. Now up here, the radius, by definition of a radius, by the definition of a radian, our radius is actually per 1 radian. This is optional to write the per 1 radian, but just so you know, that is true. So if I were to use my radius here, it would be 2.5 feet for my radius. And technically, that is per 1 radian. If you want to include that, so you can see how our units are going to cancel out. So we're going to multiply that by our angular velocity. Well, we have radians per minute, we have radians per second, and we have degrees per second. Okay, we can use any of those because those are all our angular velocity. But since I want miles per hour, I probably don't want to use the ones with seconds. I could. I'm just going to use our original given information. So R times omega, again, our omega is 240 pi radians per minute. Notice how this is our fraction bar, radians per minute. Now, does anything cancel? Just the radians, right? And we're left with feet per minute. But they want MPH. MPH is miles per hour. So we're just going to do a dimensional analysis here. I want to get rid of my feet, and I want to go to miles. You know how many feet are in a mile? You need to know that. So start memorizing it. 5,280 feet in 1 mile. So my feet cancel, and I'm left with miles per minute. And again, I'm doing a dimensional analysis. I want my minutes to cancel, and I want to be left with hours. How many minutes in an hour? And now I'm left with miles per hour. So now that I have it all in my bridge, now you may use your calculators. So I'm going to do 2.5 times 240 times 60 divided by 5,280. If I change that to a fraction, I get 75 over 11 pi, because I didn't include my pi in there. I left my answer in the form of pi. I'm going to check that again. 2.5 times 240 times 60 divided by 5,280 gives me approximately 6.814. As a fraction, that is 75 over 11 pi. And that would be miles per hour. You may want to convert that into a form of, not a form of pi, so it makes more sense. Again, follow whatever the directions. Sometimes it'll say leave your answer in the form of pi. So if I multiply it all out, I get approximately 21.4199. So that would be 20 miles per hour. Approximately 21 miles per hour. And again, 21 miles per hour makes a lot more sense to you than 75 pi over 11 miles per hour. But again, follow directions, whatever it asks you to do. This is the exact, this is an approximate. Okay? All right, let's try the next example, example number 2. Again, we're going to first start by writing down everything that's given to us. A tire with a 9-inch radius. So the radius equals 9 inches. Is rotating 30 mph, 30 miles per hour. So is this linear velocity or angular velocity? They didn't tell us. Well, actually, they did tell us because they said miles per hour. Miles is a length, so this has to be our linear velocity. Because of the unit, it has to be linear velocity. Find the angular velocity. Well, that would make sense. If they give you the linear velocity, they're not going to ask you to find the linear velocity. Find the angular velocity of a point on, let's just say, its rim. So let's start with that. So you write down the given information. Okay, you can look at the steps on the previous page. Write down the given information. Include variables and their correct units. Convert if necessary. Also write a question mark for the unknown. That was step 1. We did that. pick an equation that relates all the variables to each other. So what equation do we have that puts this all together? Well, again, that's the one you have to memorize. V equals R times omega, like a little curly little W. Step 3, if necessary, rearrange the equation for the unknown. I want you to rearrange before you substitute. Okay, so it's asking us to find the angular velocity. So to get the angular velocity by itself, what do we do with the R? Well, we would divide. But because we're going to be using a bridge, instead of dividing by R in my bridge, I am going to be doing multiplying by 1 over. I'm going to be flipping over my radius and putting it in my bridge. It's the same thing as dividing by R. This is the same thing as this. Okay, so that's what we're trying to find. So now that you have all the information written down, you have the equation rearranged, you're going to put everything into the bridge. So the angular velocity, is this times this. So we're going to start with our linear velocity. And again, we're not going to write mph. We're going to do miles. And then this is our fraction bar per hour. You're not going to have a fraction up here. Miles per hour. And then we're going to multiply by 1 over the radius. So here's the radius. We're going to multiply by 1 over 9 inches. 1 what? Well, again, technically, it's per 1 radian. It's up to you whether you want to write that or not, but it does help with the dimensional analysis if you do. So that's what we have. What cancels? Nothing. So why doesn't it cancel? Well, because you have miles here and you have inches here. And if you don't write down your units, you would never know that. So we need to cancel miles and inches. So again, we want miles to disappear and we want inches to disappear. So if the miles are on the top, we're going to put miles on the bottom. Now, do I know how many inches in a mile? I don't. I know how many feet are in a mile, so let's start with that. 5,280 feet in 1 mile. So mile cancels miles. Now feet in inches, those don't cancel, so I'm going to keep going. I want my feet to cancel, so that goes on the bottom. I want my inches to cancel, so that goes on the top. So 12 inches in 1 foot. Sorry, I might run out of room here, so I'm going to rewrite that. 12 inches, 1 foot. So feet cancel feet, inches cancel inches, and I'm left with radians per hour. Radians, is that theta? Radians per hour? Radians per unit of time? Is that angular velocity? Yes, it is. Radians per any unit of time is angular velocity. Okay, so my angular velocity, I'm going to use our calculators. We have 30 times 5,280 times 12, and then all divided by 9. Oh, that's a big number. 30 miles per hour, or angular velocity. Double check that. Miles, miles, inches, inches, feet, feet, right? 30 times 5,280 times 12 divided by 9. All right. So I end up getting 211,200 radians per hour. That, again, radians per hour, let's keep going with that. It says express the result in revolutions per minute. Maybe that'll make a little bit more sense to us. So again, let's do a dimensional analysis. If I have 211,200 radians per hour, they want me to convert it to revolutions per minute. So I need my radians to cancel, and I want revolutions. So what do I put where? One revolution is 2 pi radians. So now I have revolutions per hour. And it's asking for revolutions per minute. So I want my hours to cancel and be left over with minutes. So 1 hour is 60 minutes. Now I want you to practice doing this in your calculator, because this is the one that people tend to get wrong because of this in the denominator. So practice typing it into your calculator and see if you can get the correct answer. You should end up getting 560.225 revolutions per minute. That seems like a lot. 560 revolutions in a minute if you're going 30 miles an hour with a 9-inch. I don't know. I'm going to have to check that one. Pretty fast. Okay. All right. So if you didn't get the 560, I recommend using your fraction bar on your calculator, because if you don't and you do 211,200 divided by 2 times pi times 60, your calculator is going to divide by 2, and it's going to multiply the whole thing by pi and by 60 if you don't put all of this in parentheses. So that's why you need to practice how to type that into your calculator. Okay? All right. Next. Last problem. This problem is different than the one that is in your notes. I don't like the one that's in your notes, so we're going to switch it. Okay? All right. So just cross that one off. It says 2 pulleys connected by a belt. So the first thing I'm going to do is I'm going to draw the best that I can. It's like think of it as like a chain around on a bike. Okay? And one has a radius of 15 centimeters. So I'm going to call that radius 1 equals 15 centimeters. And over here, we have radius 2 equals 8 centimeters. So again, I'm just breaking down everything that's given. The larger pulley rotates 24 times in 36 seconds. Rotates. Angular velocity, linear velocity. Which one? Rotates 24 times. Well, it's not a length, so it can't be linear velocity. So maybe angular velocity, so the larger one, and again, we can call this the larger one, and we can call this the smaller one. So the angular velocity of the larger one is 24 times, or 24 rotations, or 24 revolutions per 36 seconds. Times, rotations, revolutions, all the same thing. However, we cannot call this angular velocity because it's not radians. So this is where we have to do a conversion before we can call it angular velocity. So what is the unit conversion you put in there? 1 revolution is 2 pi radians. Okay, so if we reduce this, we end up getting 4 pi over 3 radians per second. Leave everything in the form of pi for right now. So reduce, that reduces to what? 2 over 3? Yeah, 12 goes into both of those, so that would be 2 over 3 multiplied by 2 pi, that gives you 4 pi over 3. Or use your calculator if you have to. All right, so we know the radius of the larger one, we know the angular velocity, that is the rate at which that angle rotates. This is a smaller gear, so the angle is going to rotate faster. You have a smaller gear, so you have to rotate faster to keep up with this one. They're attached by a chain, or in this case, by a belt. They're attached by a belt. So let's see what it asks us to do. I wrote down everything that's given. I drew a picture. Find the angular velocity of the small pulley in radians per second. That's what it's asking us to find. So what are we missing? In order to find the angular velocity, you have the radius. What else would you need? You would need the linear velocity. But they don't give it to us. Or do they? Let me ask you this. If there was a point on this belt, and there was a point over here, and the gears were turning, would this point move faster than this one? If this started moving, could this move faster or slower? If this is the same belt, doesn't this point have to move just as fast as this point over here? So what does that tell you? This point moving is linear velocity. This point moving is linear velocity. Linear velocity is the same. It's not going to change. So this V is also this V. They're the same. So we actually are given the linear velocity. So let's go ahead and calculate the linear velocity with this information. Again, V equals R times omega. So we have 15 centimeters per 1 radian. Again, that's optional. Times our angular velocity of 4 pi radians per second. So the radians cancel out, and we're left with centimeters per second. Length over time matches linear velocity. So if we just keep it in the form of pi, that's 15 times 4, which is 60 pi centimeters per second. So the linear velocity is the same because it's the same belt. So now we can answer question A. Find the angular velocity of the smaller pulley in radians per second. So V equals R omega. So omega is V times 1 over R, just like in the last example. Okay? So the angular velocity of the smaller one is the linear velocity, which is 60 pi centimeters per second times 1 over the radius, or this radius flipped over, which is 8 centimeters per 1 radian, again, if you want to include that. And notice the centimeters cancel, and we're left with radians per second. Now it wants radians per second, and we have radians per second. So we're done. If we use our calculator or we reduce, that's going to be 15 pi over 2. 60 over 8 reduces to 15 over 2, and that would be radians per second. If we wanted to approximate that, that would be 23.562 radians per second. Okay. So again, the speed at which the point moves around this pulley is the same speed as it moves around this pulley because it's the same belt. And one piece of the belt can't move faster than another piece. Okay? So part B asks us to do what? Find the linear velocity of a point on the belt that connects the two pulleys in centimeters per second. Well, we already have the linear velocity. Well, that's weird that they did it for part B. Those probably should have been switched around because we actually already did part B. Linear velocity of the point on the belt that connects the two pulleys in centimeters per second. So we already did that. $60 pi centimeters per second, or approximately 188.4955 centimeters per second. Okay, and that should help you with one of the problems in your assignment. And that is linear and angular velocity. If you need to, rewatch the video. Make sure you follow the steps 1 through 6, show your work neatly.